is elementary matrices and elementary row operations. And elementary makes it sound really easy, right? So guess what this section is not? It is not easy.
It's like Sherlock Holmes saying.
Yeah,
elementary.
this is like the most confusing chapter I think in the whole book, and I almost gave up on ever teaching this class because of this section. So, if you're confused, don't worry, give it some time, let the material sink in, and we'll eventually get there. So, elementary matrix, okay, in 1.1, we talked about there are three different operations we could do, elementary row operations, right? We can interchange, we can multiply by some non-zero, or we can add a multiple. So we're going to use the matrix multiplication now to perform those operations. So an elementary matrix, it's one that can be obtained from the identity matrix through a single elementary row operation. Literally one thing, just one thing. So each elementary matrix, it's square, and it has an inverse. When determining if a matrix is elementary, we begin with the identity matrix, and then we see what single operation can be done to the identity matrix to obtain the given matrix. So, identity matrix, ones on the diagonals, zeros everywhere else. You're going to have a matrix where one of those elements is not what it should be. And it can only be one, otherwise it's not an elementary matrix. Okay, you know how sometimes we can do adding multiples for two different rows at a time? One only. Okay. Elementary matrices are useful because they enable you to use matrix multiplication to perform elementary row operations. This is where it gets confusing. How easy is it to multiply matrices? It's actually kind of confusing, right? It's the pat the head, rub the tummy at the same time. It's not elementary. I would way prefer to do elementary row operations and multiply matrices. So this is part of why this section's so confusing, is it's counterintuitive. Why would I make my life confusing when I know I can perfectly easily do this problem in a much easier way? So why is because it's setting you up for future sections of what you're going to be able to do, okay? So just know that it's going to be frustrating because you're going to say, but why can't I? Okay, you can, but in this section we're not. Okay, so just have that understanding that we're taking something that you already know how to do and we're doing it in a different way, and it's more confusing. But it's a different way of doing something, which means we're learning. So let's look at examples of elementary matrices. Is this one an elementary matrix?
No.
Why?
Well, because of the one, there's no one.
Okay.
Yes.
Remember, it's the identity matrix except for one element.
Except for one.
Except for one element. This one has ones on the diagonals except for the 3. Everything else is 0. So yes, this is elementary. The key is if I want to take the identity matrix and make it look like this, what would I do? Take row 2, multiply it by 3, and that would give me this matrix.
Why would it be 3? Why would it be not 1/3?
So you're going backwards. So the way they're asking the question is, take your identity matrix, what do you do to the identity matrix to
okay.
get this?
Okay.
And this is also why this section is so confusing.
So don't look at what you've done.
Exactly, because you want to say, well, multiply the second row by 1/3 and I got the identity matrix, right? That's
Yeah.
how your brain has been trained to think of this, and you're absolutely correct in thinking that way, that we're in this section. So the way they want you to think about it instead is, start with the identity matrix and how did I go from there to here? And don't worry, we'll go back to there, it'll be okay. All right, what about this one? Is it elementary or not?
No.
No, because
It's not square.
it's not a square. What about this one?
Yes. No.
Well, you can't change zero.
There's only one thing that's different, right? Yeah. But the problem with it is because it's a zero, you have to multiply the third row by a zero. And elementary has to be a non-zero that you would multiply it by. Does that make sense? So, of course, math always has the exception. And there we go. Here I tell you, oh, you just have to have one in the diagonals and everything else is zero and one element. This is an example where one element's different, but it's still not elementary because to get here you'd have to multiply by zero. And we can't do zero because it has to be non-zero.
And that's goes for everything we've done so far, hasn't it? I mean, we've never been
Yeah,
used a zero.
because if you multiply an equation by zero, what do you get? Well, zero equals zero. Great. That's what have I learned? Nothing. It literally takes away information that you do know.
Why couldn't you multiply the second one by 1?
If I multiply the second one by 1, I still get the same row. Oh, you mean add.
But how?
You mean take row, no, because then the one's in the wrong location.
So up in the top it was elementary because you multiplied the second row by 3.
Correct.
Why couldn't it be multiply the second row by 1 in that bottom one?
If, you mean the third row?
No, the second.
If I multiply the second row by 1, I just get the same thing.
We need that zero right here.
You need this to be a 1.
It's because it's all zeros in the bottom. That's why this is different.
It's because it's all zeros, and the only way to get from the identity matrix to zeros all in the bottom, in this scenario, okay, not everything, just this scenario, would be to take that third row and multiply it by 0. And that's against the rules, because we have to do it by non-zeros. Told you, it's a fun one. Okay, what about this one? Is that elementary?
No.
Here.
Oh, yes.
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 Yeah.
Why?
You can switch here.
Yeah, you just have to switch those 2 rows.
That's one.
One elementary row operation. Yeah, see, sorry guys, I warned you that you're gonna have to help me tonight. So it's not true, one element is wrong. You can have more than one element wrong, right? It's just the key is one operation to make it right. Does that help? Okay. What about this one?
Yes.
Can only
Oh,
be
two.
one thing, right? Like here, it would be times 2, but this would be times -1, and that's 2 elementary row operations, so no, that's not considered elementary. When they say elementary has one operation only, they mean one operation only. Okay, one thing only at a time. Okay, now this equation is super, super important. It's a final question. Well, or version of this. Hint, hint. Remember how we can take matrices and we can do algebra to an equation with matrices? We're doing that in this section. So if I take this equation, I can rewrite it like this. How do I get from here to here? What have I done? I've divided this side of the equation by EK, E2, E1. If I divide this side, then I divide this side by it. That's how I get to those little -1s, right? 1 over. Now, the order matters, right? Order matters when we're multiplying inverses. So this is really important to notice this. On this side, I go from highest number to lowest number. When it's the inverse side, it's lowest number to highest number. Really important.
Can you see that one?
When my elementary matrices are on this side of the equation, I'm going from the highest number to the lowest number. And when it's the inverse of those elementary matrices, I'm going from lowest to highest. Okay? Super important. Now, I can simplify this equation just a little bit more. What is anything times the identity matrix?
The inverse?
Itself. Okay, so A times the identity is just going to be A. A times B times the identity matrix is A times B. So in this equation, do I need to have the identity matrix at the end? No, because it's just equal to all of that. So, guys, this is a true statement. This is taking that equation, doing algebra to it by solving for A. If I solve for A, that means I'm going to divide by all those little elementary matrices. If I divide this side by all those little elementary matrices, I have to divide this by elementary matrices, all of them. And then how do I write that? With matrices, instead of leaving it as a fraction, because can you imagine dividing matrices? Because multiplying matrices isn't very fun. So instead of thinking of it by dividing by all those matrices, we turn them into the inverses, which is the same thing. Okay, it's just a different way of writing it. And then because anything times the identity matrix is itself, we can then go to this statement. Okay, so A can be made up of a series of elementary row operations, is really what we're saying. Okay? Are we kind of okay with this? This is a section where the first time I go over something, you're probably not going to be okay. It's probably going to have to go through a few iterations and through some of the problems before it clicks. Now this is an example. I'm actually going to go over it, this example. I'm going to do it from scratch with you. When I was trying to figure out this section, I found a video, and this is how they got it, and it finally helped my brain click as to what we were doing in this section. This is all taking this equation and then making it look like that. And I'll show you after the PowerPoint. I'm actually going to do this with you. Okay, so here's that basic equation, right? All these little elementary matrices times A gives me the identity matrix. So before we solve for A, right, I'm going to instead change it. Instead of solving for A, I'm going to have all these little elementary row matrices equal to the inverse of A times the identity matrix. What did I do? I want to get these isolated, so I divided by matrix A. If I divide matrix A on this side, I divide this side by matrix A. When we divide by matrices, we don't write it like that. We write them as the inverse. Everyone okay so far? Now the inverse of A times the identity matrix is the inverse of A. So in the first one, we solved for A. And if we solve for A, what is it equal to? It's the inverse of all those little elementary row matrices. In this equation, it's taking all of those elementary row matrices, and it's equal to the inverse of A. So you see the difference between the two equations. They are all based on this equation, both of those. So in this section, that's another thing that makes it so confusing, is you're dealing with these little matrices, you're dealing with A, and on top of that, you have to say, well, are you solving for the inverse of A? Are you solving for A? Do you see how you have to be really careful about what you're given and what you need. Because sometimes these little elementary row matrices, you want to keep them as they are. And other equation, we need to find the inverse of each one of those. It's confusing. And then on top of that, the order matters, so you have to remember, I start with the biggest to the smallest, or the last to the first. And in the other equation, I have to go, if it's on this side, first to the last. Okay, so just kind of keep in mind all those things that are going on these. Okay, so here's an example of using matrix multiplication. So here we have an elementary matrix. Tell me what's elementary about this. What is the one operation that's been done?
Change row 1 to row 2.
Row 1 and row 2 have changed. Only one thing is done, just the interchange of those two rows. If I interchange my identity matrix, just those 2 rows. So it's an elementary matrix. So it went from identity matrix to an elementary matrix. Does that make sense? We started with identity, now we're at elementary. If I take that, I multiply times matrix A, what is the end result? Matrix A is exactly the same except what? The first 2 rows are switched. So there's a relationship between these elementary matrices and what happens to the original matrix.
So it goes from an identity to an elementary only because you've done one thing to it.
Because you've done one thing to it. So remember how I kept saying every section we kept talking about the identity matrix, and yet we weren't doing much with them, right? We were really going, okay, if it's 3 by 3, it's I to the 3, and it looks like this, and that's kind of all we've done. But yet super, super important, because you have to know that that's what you're always comparing to. Always comparing to the identity matrix, which means you have to know what the identity matrix is. So in this case, it's a 3 by 3. We know that it normally would have 1 on the diagonals and everything else was 0. So what is the one thing that's different? Those 2 rows. And remember, when I say one thing that's different, I mean one row operation that's been done to it. And then remember, and you gotta keep in mind what are the 3 row operations that we can do, because there's only 3. We can switch rows. We can multiply by some non-zero, right? Can't multiply by 0, but non-zero. And then the third one is add a multiple. And the adding the multiples is it's a little confusing, right, of all the 3 operations. Those are the only 3 things we can do. So if this is going to be an elementary matrix, it can only be one of those 3 options.
So really what you're seeing there though is your elementary one,
Yeah.
and then you can change it into an identity matrix.
You're comparing to the identity matrix.
Okay. But you have to make that.
You're
When-
always going to be
when
comparing.
When they multiplied them, they actually did it by switching things.
When they didn't show you all the work, all the steps.
Okay.
If
That's
you
what I-
literally take this matrix times this matrix,
You
right,
get-
you get 0, 1 plus 0. There's the 1. You see, you literally are multiplying these 2 matrices. And when you literally multiply these 2 matrices, the cool thing about these elementary row matrices is that literally whatever that elementary matrix is compared to the identity matrix is the effect it's going to have on that matrix that you're multiplying it by. They literally do that to that matrix. If I were to start with the identity matrix and have a 2 here, which would mean what? I multiplied row 1 by 2. I would find that this would be 0, 4, 2 when I multiplied it by the elementary matrix. What you do with that elementary matrix times whatever matrix you're multiplying it by, that 1 row operation will happen to that matrix.
It takes care of itself.
It takes care of it. It's literally it literally happens. Like, yay, okay.
It's like magic.
This is so much fun. Okay,
I'm
so,
saying 0 times 0 and you got a 1.
well, that's why we can't multiply by 0, right? It has to be a non-zero.
Right, no, but if you take those 2, you start out with the very top one. It would
Yeah.
be 0 times 0, wouldn't it?
Now remember, 0 times 0 plus 1 times 1 plus 0 times 3.
Oh, okay.
Okay?
Yeah, I was forgetting.
Yeah, pat the head, rub the tummy. Yeah, exactly it. Okay, and make sure that we multiply A on the left by the elementary matrix. Order matters. If you have A times E, it's not going to work, right? Because order matters. So those 2 equations that I have double underlined, okay, when you use those, write them down because it matters which order you're doing it. And then also matters if the A is going to be inverse or if the elementary matrices are going to be in the inverse. Those two equations, everything is derived from those two equations. Okay, now we're gonna talk about the difference between row echelon versus reduced row echelon. We did this already, right? But guess what? It takes on a whole new importance in this section. Because what the book won't tell you is some of the problems you have to get into reduced row echelon form. And in other of the problems, you do not get it in reduced row echelon form, or you will not be able to get the right same answer in the back of the book. It never states that. I will state it. Okay? I will tell you.
You don't know which
Nowhere, and what's really frustrating is in the book, is there are examples, all just happen to be reduced row echelon form. It just so happened to be that way that when you get it into row echelon, it turns out that it's actually a row. So that is the stumbling block that took me, I don't know how many hours to figure out, because I could never get the same answer as the back of the book, even when I thought I understood what I was doing. And I did actually understand what I was doing, it's just that there's a difference between these two. And this section, it matters which version you want to do it. And then to really make it confusing at the very end, I'm going to talk about L and U, and those are a whole nother form. But it's okay. We're going to get there. It's going to be all right. Okay, so row echelon form. I need to have leading ones, right? And then everything else below, 0. But on reduced echelon form, I have the leading ones. But what has to be above and below those ones? Zeros. In row echelon form, I do not have to have zeros above it. Are we kind of okay with that? That is the difference between row echelon and reduced echelon form. The leading non-zero is still a 1. The reduced echelon, still leading non-zero is a 1. Zeros below the leading non-zero number. Zeros below the leading 1. But in row echelon form, we do not need zeros above the leading non-zero value. But we do in reduced row echelon form. So this distinction is really important. Remember how at first I was telling you that understanding reduced row echelon form is important because you need to know when you can stop? Okay? Kind of has to do with that. You gotta know when to stop in these problems. Okay, now we're gonna talk about lower triangular and upper triangular. Okay? Now, here's the cool thing about lower triangular. Tell me what you notice about it. Why is it called a lower triangular? I got a little right triangle on the bottom, right? On the low part. So, do I need 1 leading ones? I do not need leading ones. What I do need is I have numbers on the values on the diagonal, but what is above those? Zeros. That is what makes this a lower triangle. When I'm looking at the upper triangle, do I need leading ones? I do not. But what do I need? Zeros on the bottom. Okay? Questions on those? So now we've got row echelon form, we got 1s, and we got zeros, but we don't need zeros up above. We have reduced row echelon form, which is 1s, zeros on top, zeros on bottom. Then we have lower, don't need 1s, but we need zeros on top. And then we have upper, don't need 1s, but zeros on the bottom. You got it?
Got it.
All right. Remember, I'm really kind. I do these for you, okay? I got it on one spot for you. Okay. So there's kind of the key ones we need to talk about. All right, now let's talk about row equivalents. Matrices that can be obtained from one another by a finite sequence of elementary row operations are said to be row equivalent. And if A and B are row equivalent matrices and A is invertible, then we know that B is invertible. Okay, so what's that say? It's saying if I start with a matrix and I do a whole bunch of elementary row operations, which like one thing at a time, right? Okay, and I get another matrix, they're row equivalent. And basically, what do I always show? That indeed, every time we've been doing this, they're row equivalent. The little squiggly ones, right? And if A and B are row equivalent, if one is invertible, then the other is also invertible. Does that make sense? Because they're basically what? The same matrices. They just look different. Does that make sense? They really are the same matrix, just look different.
What makes them the same?
All those elementary row operations. Any row operation I do I actually change any values? It's like fractions. If I have 4/5 and I multiply by 5/5 and I get 20/5, have I changed the value of that fraction? I've changed the way it looks, but have I changed the value of that number? That is exactly what we're doing with row operations. We have an equation, we're multiplying it by some non-zero, we're changing two rows, we're adding a multiple. None of that changes the actual values of any numbers. That's why we're able to take these matrices and actually do the augmented part with what they're